Hello, welcome to the Chapter 19 review guide with answers. Now in this video, I am not going to go over the entire review guide. I'm not going to go over the part from the top where it's just following along with the PowerPoints and the videos that I've already made. This is just going to go over the stuff below the line, which are basically self-test things to see if you are ready for the test. So let's start with the vocabulary. Matching, know these definitions. Know the difference definitely between electrical potential and electrical potential energies. EPE, or electrical potential energy, is the work done by the movement of an electric charge. Okay, so if I have work, work is equal to the change in electrical potential energy. So the difference in electrical potential energies is equal to the work done, just like the difference in gravitational potential energy is equal to work, and these are both in joules. We'll also know that electrical potential energy is equal to the charge times the voltage difference. And this delta V, that delta V is the electrical potential. So if I take the electrical potential energy per unit charge, or basically take volts equal or potential difference, I could say that this is equal to, I don't have it, the triangle, delta EPE divided by Q. Space there. So that the change in EP divided by Q, I'm just rearranging this part of the equation. And that's what voltage is. And voltage, electrical potential is what we measure as volts. Electrical potential energy is an energy and it's measured in joules. Energy per coulomb, joules per coulomb is a volt. All right, now voltage is a conservative force, and what that means is that the path does not matter. All that matters is how far you displace yourself in the electrical field. If you move along an electrical field line, and I'm going to get to those in a moment, then you do no work. You have to move along the electric field itself, not the equipotential surface. Sorry, I said electrical field line. If you move along the electric field line, you do work. If you move along an equipotential surface, you do no work because the potential didn't change. Delta V is 0 if you move along an equipotential surface. All right. So what is a volt? A volt is the SI unit of that electrical potential. Oh, and I didn't really make it clear, but conservative force means that the path does not matter. So it doesn't matter how you get from point A to point B. All that matters is where point A is and where point B are. Other examples of conservative forces are gravitational potential energy. A good example of a non-conservative force is friction, because the longer the path, the more friction. But if I just go in a circle, I can start and end at the same spot. And if I start here and end here, I've done no work. But I have gone against friction. So friction being the non-conservative force that cares about the path. But for voltage, electrical potential energies, they are conservative. The path does not matter. And I've given many videos on that, or at least parts of videos. A dielectric, what do I want you to know about a dielectric? A dielectric is, by definition, an electrically insulating substance. However, if you place these dielectrics within a capacitor, they can be used to raise the capacitance. So those are the two things I want you to know about that word. And then lastly, I don't want you to get volt with electron volt confused. An electron volt is not equal to 1 volt. An electron volt is the magnitude of the EPE of one electron moving through a potential of 1 volt. So if I move one electron over a delta V of 1, that's an electron volt, right? But an electron volt is not a volt, right? Just make sure that you understand they're not the same thing. And I talk about that in the earlier videos as well. All right, so I threw some equations here. You're welcome to look at those, but let's talk about things you need to know. Electric field lines were in the last chapter, so you should already know about them, but keep in mind that they are everywhere perpendicular to the associated equipotential surfaces. That's this chapter's topic. They always go from plus to minus. Closer lines mean higher magnitudes, and a few other things I didn't put on there, but electrical potential is tangent to it. So the field lines are basically anywhere on that field line points in the direction of the electric field. They never cross, and the more lines you have, uh, the number of lines is proportional to the electric field strength. So if I'm going to use a drawing where I have a +3 charge and a -1 charge here, there have to be 3 times as many lines coming out of the +3 as there are going into the -1, because the +3 has 3 times the potential of the -1. And the other 2/3 of the lines would have to go somewhere else. Now, rules for equipotential surfaces, which were new in this chapter, and those were kind of like, you know how you had the red lines were the electric field lines, and then you had these circular blue things. Those circular blue lines were the equipotential surfaces, and they always surrounded the charge. And they have rules too, and they're basically the same rules in terms of like conceptually. They're always perpendicular to the electric field line, and the electric field lines are always perpendicular to them. Just like the electric field lines have to be perpendicular to the charged surface, the equipotential surface acts as an extension of that surface, so the electrical field lines have to be perpendicular to the equipotential surface. They do not intercept, and intersect, not intercept, and the closer the lines are, the greater the magnitude shift from one line to the next. So it's a denser field area. Now remember, for electrical potential work to be done, you must move closer or farther to an equipotential surface. And it's a conservative. It's a conservative, so the path doesn't matter. But if all I do is move along an equipotential surface, I do no work. That's like moving along a shelf. And I tried to explain in class that if I had a shelf that went all the way around the Earth, but stayed the same distance above the Earth, it might look flat from where you are, but it's really a big curve, just like an equipotential surface is a big curve. And as long as I stay on that curve, I don't do any work. All right, so how do we add these? We add them as vectors. These are vector quantities. How does the magnitude of the charge in the plates of a capacitor relate to the magnitude of the potential difference between the plates? So if I go down here a little bit, you'll see, remember the equation is Q is equal to CV. Charge is equal to capacitance times electrical potential. So how does the magnitude of the charge, that's Q, of a capacitor relate to the magnitude of the potential difference? That's the V. Well, it's directly proportional. If one increases, so does the other. It's like Q is equal to CV. They are directly proportional. If one goes up, they're on opposite sides of the equation, so the other one has to go up. The work done by an external force in moving an electron at constant speed between 2 points in an electrostatic field depends only on, so think about that, it's work, and work is force times distance or displacement. So it's just the same kind of work. It only depends upon the displacement of the charge, because it's an external force, so it's that force times the displacement of the charge. So keep in mind that voltage is work per unit charge. If we go up here, we see that work or volts is equal to delta EP over Q, and delta EP equals work. So right here, volts is equal to delta EP over Q, which is the same thing as work per unit charge. So voltage is work per unit charge, and work is force times distance. If the charge doesn't change, then the only thing that is left is distance. It's only distance that matters. Now that also means that really only the distance against the field line and not parallel to it. Because remember, if you move along a field line, I'm sorry, I keep saying field line. And what I mean is equipotential surface. Displacement against the, I'm going to write that in, equipotential surface, and not parallel to it. So if you move parallel to an equipotential surface, you don't do any work. So it's displacement against the equipotential surface is really what matters. All right, we're getting there. Hope you're following along. Two positive point charges are separated by a distance r. If the distance between the charges is reduced to 1/4 r or increased to 4r, for examples, what happens to the total EPE of the system? Well, work is equal to the change in EPE, which is equal to KQQ over R. Since you are dividing by R, not my R, but by R, if you increase the distance to 4R, you're now dividing by 4R, so it becomes 1/4. It's directly related. Okay. So let's do some example math, all right? The electrical potential at a certain point in space is 6 volts. What is the electrical potential energy of a -3 microcoulomb charge placed at that point? So remember, 6 volts is electrical potential, not electrical potential energy. And EP is equal to the charge times the electrical potential. So if I know the charge and I know the electrical potential, I know the EPE. So -3 times 10 to the -6 times 6 leaves me with -18 microjoules. Next, a completely ionized beryllium atom, net charge +4e, is accelerated through a potential difference of 3 volts. So I have a potential difference and I have a Q. What is the increase in kinetic energy of the atom? Now remember that we were talking about energies and how now we had 5, and actually we're up to like 6 now, but you can use the conservation of energy. In this case, loss of potential energy has to equal the gain in some other type of energy, and the gain in energy here is basically velocity. Just like when I lose gravitational potential energy, I can create velocity. If I lose electrical potential energy, I can create velocity. All right, so I know the potential difference, that's the voltage, and I know the charge Q is equal to +4e, delta V is 3 volts, and I know loss in potential energy equals gain in some other energy. Well, so delta KE is equal to delta EPE, and delta EPE is QV. Now that Q was given in electrons, not in what the actual charge was. So to get the actual charge, I would take, I don't know why I have 12 and not 4, because it's 4 electrons. But I want the illums. It should be 4 electrons times 1.6 times 10 to the -6. That would tell me how many coulombs I have. Yeah, I'm like, I did the 3 twice there. We'll change that to 4. And so it's 4 times 1.6 times 10 to the -6. That's per electron volt. I'm converting it from charge to, that's not electron though. Yeah, don't worry what I have here. It's just 4 times 1.6 times 10 to the -6 coulombs to convert it to coulombs times 3 volts, which would be 12 times 10 to the -6. Well, 12 times 1.6 times 10 to the -6. So I didn't work that out properly when I was doing this before, but hopefully you're following along with me as I make these corrections. So that would give you your answer, whatever 12 times 1.6 times 10 to the -6 is. Okay, because you have your Q, your charge, and you have your volts. Next one, if the work required to move a 0.5 coulomb charge from point A to point B is 145 joules, what is the potential difference between the 2 points? So I've given you work, so I've also given you delta EPE because they are equal, and I've given you I've given you the amount of work and I've given you the Q. Q is the charge. So I know Q is equal to 0.5 coulombs, work is 145 joules. Work is equal to Q delta V, so delta V is work divided by Q, 145 divided by 0.5, 290 volts. It's because potential difference is volts. So when you see potential difference, think volts. If you see electrical potential energy, think, or just electrical potential energy, think joules. Potential difference or electrical potential are volts. Electrical potential energy is joules. If I mess that up at any point, let me say it one more time. EPE, electrical potential energy, is joules, it's energy, which is the same as work. Volts, which is, I could say potential difference, or I could call it electrical potential, but without the energy at the end, those are measured in volts. And work, which is equal to delta EPE, is equal to Q times delta V. All right, moving on. 2-point charges are arranged along the x-axis as shown in the figure you will be given. So these lines here, I would tell you what x is. So you would know what the distance is between them. Okay. At which values of x is the potential equal to 0? Note at infinity the electric potential is 0. So I have a charge here, and that charge is 2 microcoulombs. So I made these up. So let's pretend that this charge, first one, is 2 microcoulombs, and Q2 is -4 microcoulombs. And either the voltage is KQ over R. It's another way of defining voltage, because I'm asking about the electric potential. So I want the electrical potential to be 0. Now, since I have 2 charges and I want to know the net charge, I add them together. And I add them like vectors, but since they're on a line, there's only one axis, so I can just add them. So voltage of Q1 would be KQ1 over R, and then KQ2 over R2 for the second one. So I would have, this would be like R1 and this would be R2. And I can't have, that would be 2 variables in one equation. But I can replace R1 with X, and then R2 has to be 1 minus X. And X would be whatever the distance is between these. So if there was like a distance of 4, I would replace X with 4. And then this would, you know what I mean? Yeah, just leave it as X right now because I'm probably not going to give you a value there. So I know that Q1 divided by X plus Q2 divided by 1 minus X has to equal 0 because I want to know where the electric potential is equal to 0. All right, and the K's cancel because the K's are the same. And I'm replacing the R's with X and 1 minus X because the total, if I make the total distance 1, right? I think I said that wrong, so let me start over just so you understand. If I say this charge is 2 microcoulombs and this charge is -4 microcoulombs, and we know that volts are equal to KQ over R, I know that the sum of these two the sum of the potentials between each of these points must be 0 because that's what the question asks. So KQ1 over R1 plus KQ2 over R2 has to equal 0. All right. Now, if I pretend that the distance between these 2 points is 1, so this 1 right here, if I change that 1, if I change the distance between these 2 points, I would replace 1 with whatever that distance is. And the K's cancel because I can just divide by K. So I end up with Q1, the charge of this one, divided by X plus Q2, the charge of this one, divided by 1 minus X. Because if the whole distance is 1 and I make this part X, then the remainder has to be 1 minus X. So I know what Q1 is, it's 2. I know what Q2 is, it's -4. I put those into the equation. I solve for X and I get X is equal to 1/3. Which makes sense because this is a 1-to-2 ratio. 1 plus 2 is 3. So 1/3 of the way should be from the 2 microcoulomb because it's the lower charge, so I need to be closer to it. And it's a direct relationship. So if it's a 1-to-2 relationship in the charge, it has to be a 1-to-2 relationship in the distance. So I divide the distance by 3. I go 1 from this point and 2 from that point. So you could do this conceptually is what I'm trying to say, as well as mathematically. All right, next one. The magnitude of the charge on the plates of an isolated parallel plate capacitor is doubled, tripled, cut in half, something to that effect. Which one of the following statements is true concerning the capacitance? So I'll tell you a whole lot of things, I probably will, and then one of them will be no effect. And the answer is no effect. Capacitance is a capacity, okay? In order to change the capacitance, I would need to change the capacitor itself, change the distance between the plates, change the size of the plates, or add a dielectric, right? Changing the amount of charge on the plate won't change the capacitance. At some point, I will hit the maximum amount of charge, and I won't be able to add any more. but I can't change the capacitance. That's a capacity. It stays the same unless I change the capacitor, such as changing the plates, changing the distance between the plates, adding new plates, or adding a dielectric, which leads us to the next question. A parallel plate capacitor with plates of area A and plate separation D is charged so that the potential difference between the plates is V. So I would give you numbers in A, D, and V. And we have an equation for capacitance. And I don't even know if I put it on here because we're not using it. Let me double check up here. Nope, it's actually even a blank right there. The capacitance of a parallel plate capacitor filled with a dielectric is C is equal to, and there's this equation that takes into account all of these variables, A, D, and V. But what I'm asking is, what is the magnitude of the electric field if a material with a dielectric constant D is inserted between the plates? Well, all you need to know is that Q is equal to CV. I don't need to know what C is. I just need to understand that adding a dielectric will increase C. Whatever values I put into that equation, D, V, A, and K for the dielectric constant, whatever they are, they're going to increase the capacitance. Now I'm not changing the charge. So if I increase the capacitance, voltage has to decrease. So really all you need for this equation is understanding Q is equal to CV and understanding that if I add a dielectric, C goes up. So that's the review, going over just the things on the back. As always, if you have questions, let me know. If you're missing blanks from the study guide anywhere, just let me know, and I will try to help you out. That's it for now. Bye.